Assalamualaikum warahmatullahi wabarakatuh. Now we move to the second last chapter for this semester. It is another different theory, which is producer theory. So we are done with the consumer theory. Now we move to the second part of entity in the economic study, which is very, very important also, that is producer. Now before I proceed to the specific topic of producer theory, if you can recall back, in your very basic economic study, so we have two parties in the economy, in an economy. Yeah? So this is household, and then this is firm. What we understand is that in this very simple economy, private closed economy, because when I say private, we don't have government. When I say closed, we don't have international trade. So we only have private sector in this economy, household, and also firms. So if you can recall back in your principle or basic of economic study, household will provide all the inputs to the firm. So we have inputs here, so that firms in the economy can use these inputs to produce goods and services, and then sells back to household. So here, in return, household will receive product or goods and services. So this is what we call circular flow, right? All right. Now, when we talk about household supplying inputs to firms, recall back that when we talk about inputs, we have four different types of input. The first one is entrepreneur. The second one is labor. The third one is capital. C, not K. Capital. Entrepreneur, labor, capital, and the last one is land. Land. Okay, but of course we can have raw materials here, but this is the very basic thing that you learn in your first year. But anyway, the most discussed inputs in the study of economics are two. They are labor and capital. So usually labor is denoted as L and capital is denoted as K. Right. So this is the basic that I want to emphasize. So here, like I said earlier, firm receives input from household, so that firms can use these inputs to produce goods and services or products. So if we take a firm in an economy, or we call it a producer, so this firm carries out the production process, okay, and then in the production process, this firm transforms these inputs that it receives from household into output or product. So this is another term, output. Product, goods and services, output, they are the same thing. So in order to do this, in order for firm to be able to transform inputs into products or output, the firm must employ a certain technology. When I say certain technology, it means a certain methods in a simple English. Yeah. So just imagine we have a firm, one firm, and the firm produces one product or one output. But in order to produce one product, let's say shoes, you know that you need the person who can sew the shoes. So we need labor, obviously. But if you just have labor, then you cannot produce shoes. You need to have, the place to do it. So the place to do it is what we call factory. Then this factory can be considered as capital, and then you need what we call raw materials as well, isn't it? So here, if the firm produces a single product from many inputs, as you can see, we have many inputs here, not just one input to be used, or factor of production. Yeah, so another term here is factor of production to be used to produce this one product. Okay, so we can say that this firm is producing one product using many inputs. So we combine all of this input into one kind of method prescribed in a production function so that this can produce output. So the technology here in which this firm is using to produce one single product from many inputs is what we call production function. Okay, so please understand this basic first before you go to the mathematical part of it. Now, so this is what I said just now, point number 1, point number 2. Now, let's move to the next one here, point number 3. If we have a single firm, okay, single firm wants to produce product, okay, of course the product has its own price in the market, okay, and in order to produce a product, the firm needs to hire inputs if the firm doesn't own it or doesn't own them, okay, and like I said to you earlier, the firm can use many inputs to produce output using technology. Now, I did talk about the price, and then I did talk about output and input demands. Okay, so when we talk about the price in the production function, you can't see it clearly. So it becomes an exogenous variable in the production function. But here, we use input to produce output. Then it becomes endogenous. Yeah, these two becomes endogenous. Now the idea here is that just imagine that if you are a firm, you know that you want to produce products using certain inputs, and you know that input is not free, you have to pay, then it involves some amount of costs. After producing a product in terms of many quantity, then you want to sell that product in return with the hope to get profit. What kind of profit? As much as we could, isn't it? Then that means the firm is aiming to achieve optimal production decisions so that it can maximize profit. Otherwise, who wants to do business? We don't do business for welfare, you get me? So here, always remember, if you are a firm, when you do business, your main objective is not welfare. Your main objective is to maximize profit. So by all means, including your production strategy here, should be helping you or should be assisting you to maximize profit for your firm. Okay, so the aim here is to understand the optimal production decision of the firm so as to maximize profit. So when we say optimal production, means the level of production decision done by the firm that can maximize profit. The amount of outputs produced by this firm that can lead to maximum profit. That's why it is called optimal. If it is not optimal, it's not the best. When it is not the best, the profit that we earn is not the maximum one in it. Remember, we just want to study the production technology, production set and whatnot. We are not studying management. Therefore, we don't pay attention to organizational strategy aspects of this factory or firm and whatnot. Because the objective here is to have a model that can be transferred in its pure form, this is mistake, yeah, in its pure form to the general equilibrium framework. So when I say about the general equilibrium framework, it means what? If we have production function and at the same time the cost of inputs, why the cost of input? Because labor is not, you don't gain it for free, yeah. We don't have slave here in this century anymore. So it involves cost when you produce. Then you want to find the right amount of quantity of output, okay, to maximize your profit so that you can pay back labor, capital and whatnot. So we're talking about, maximum profit. And then of course there's some method there. So we're talking about the general equilibrium framework. Now, what's the difference between the production theory and also the consumer model that we learned earlier? In the production theory, we don't learn about income effects. And then furthermore, what is more interesting is that when consumer doesn't have enough information about the characteristic of the product, because the consumer just consume and the consumer is not producing the product. Well, for the firm, everything is observable. Therefore, we have what we call perfect information. We don't have myopic in nature. Myopic characteristic of firms and also the owner of the firm. So we are running our analysis here in a pure competitive model. Let's crack on. So we want to look at the model of production function here. Now, before we proceed to the production function, as you can see here in the term that I used here, we have production set and technology. Now, what you're gonna see in the next slide is not, production set. What you see is the production function written in a mathematical form. I go straight to the production function because this is what you can understand easily compared to production set. Later on, okay, then I'll show you a little bit about production set. What is more important is for you to understand the whole thing first, so that when I give you the mathematics, it's very easy for you to do it because you understand the concept. Okay, now let's move to the next slide. So let's look at the basic theory or primitives. So just imagine we have one firm with one production of good in a positive real number. So that means, okay, you imagine you are a firm, you want to use input. I haven't mentioned to you how many types of input, but I told you that you want to produce one output or product or good. Okay, so because we just want to produce one type of product, therefore the type of product here must be in the real number positive, like one quantity, two quantity, three quantity. We don't see that we have negative quantity of output. We don't see that way, and because it's just one product, so you can see that the superscript here, we don't have anything because it means it's a positive in number. Okay, and it is one product only. Now, to produce this one product in the production process by this firm needs input, isn't it? Now, like I said to you, if you want to produce shoes, you need raw materials, for instance. You need machine. And then you need the labor if imagine you yourself cannot sew. Or if you think that you want to sew because you know how to sew, but at the same time you want to receive some salary apart from the business that you are running, the shoes business that you're running, then you are considered as a labor. You get what I mean? So can you see here how many inputs do we have? Number 1, number 2, and number 3. That means our K here is up to number 3. So we have the input space here. This is what we call input space. Alright, so we have our input space, which is real number, and K number of input. So if we try to put it in the form of a formal mathematical notation here, let me erase this first so that it won't be a mess. Then the production function is this. A number of input, which is K, a positive number of input, which is K, and the quantity of each of the input is also positive. We don't say like, this, I'm talking about this. We don't say I have 3 inputs, let's say lint, sewing machine, let's say leather, okay? We don't see that we have K equal to 3, land here, we have negative acres of land, and sewing machine here, we have minus 0.5 sewing machines. We don't say that way. We will say 1 acre of land, 2 acres, 1.5, you get me? So it has to be positive. Now, so we have an input space which is written this way, transform into output, one output, and the quantity of output is positive, not just 0, because you imagine, yeah, if you have certain number of inputs, transform it into output, and you say, I have used a LUN sewing machine leather to produce 0 output. It's nonsense, yeah, just imagine that. I'm not talking about the ability or disability of person of sewing shoes just because he's not very good in sewing shoes. We just assume that every time we use inputs, there is an output. No inputs, no output. As simple as that. Okay, again, the basic model of production function in mathematical form is written this way, and it says we have an input space of 3 here, with each of the input quantity is positive, at least one, sewing machine, 1 acre of land, 0.5 acre of land, 0.2 acre of land, and leather, how many meters, transform into one input and one output, and the output quantity is positive using this function. What is this function? Production function. We use F. You can use whatever alphabet you want to use as long as you understand what you're saying. Usually what we see in your intermediate micro is Y as a function of, let's say, the K here, instead of 3, we have 2, capital and also labor. So what you saw in your intermediate is like this. Output as a function of K and L. Okay, output as a function of K and L. In this case, okay, positive K transform into this, and this one is Y, using function this. Okay, so here, and then that's it. Okay, that's what it means. It's not that difficult actually to read this, as long as you understand which is which. Anyway, let's erase this, otherwise it becomes a mess. Okay, so this mathematical expression here, or you can also use this, but at the master level I'm expecting you to use this so that you read a lot. So this one is actually describing the output-input combination that are technologically feasible. Feasible means it can be achieved, it can be produced using technology available in the production process of that firm. So you have some input combination, let's say 3, like I said earlier. You combine all of them into a technology, and that technology is in the production function here. And then this technology is able to produce shoes, okay? It's able to produce output. Because this technology is used with the right input such as leather, sewing machine, labor. You get what I mean? Yeah? If it is not feasible, it means what? Wrong types of input used. You want to produce shoes, you have mixer for cheesecake. Is that okay? No, it's not okay. All right. Anyway, now let's look at the property axiom 1 here. So when we talk about production here, like I said earlier, if you look at this topic, this subtopic number 1, 3.1, we say production set and technology. But like I said earlier, I go straight to the production function instead of production set. Yeah. So here, is it this? No, this one. Okay. So here, when we talk about the production function, we can look at its property in axiom 1. So axiom 1 says production function is continuous. That means if you draw a curve for production function, you don't find any gap between one point to another point. Okay, continuous. Let's say like this. This one also continuous. But if I do this, not continuous at this particular point. You get what I mean here? So production function is continuous, increasing and quasi-concave. Now, how to relate this with what you have learned in your intermediate, for instance? If the space is too small, always this. Okay, so what you learn here, if you can recall back, production function looks like this. So you have output here, you have, let's say you use labor only. It is continuous, can you see? From one point to another point is continuous. This one continuous, this one continuous. No gap at all. If I want to say that there is a gap in my drawing, I would say this way. I would draw it this way. Okay, this increasing, isn't it? Then you have a gap here at, let's say, L1. That is not continuous. So let's assume we have continuous function. So here it continues also here, and it's increasing, of course, as L increases, output increases. You can see it is upsloping and quasi-concave. This is what we call quasi-concave. Okay. Now, and by monotonicity, if y is greater than y naught, okay, so let's just assume that we have one input for simplicity, just to visualize what this crazy mathematics says about this axiom and whatnot. So I'm trying to visualize it using this graph. So let's say you have y naught is here, and then your y is somewhere here. So you can see that if y naught is here, then you have they are using y here, yeah, not yl. But here I'm using this. Let's say I'm changing it. Okay. Otherwise you get confused with my notation. That's my idea actually. Okay, so let's say idea is this. Your production function is increasing and also quasi-concave. So let's say L is here and then output here. I use Q. So if your L naught is here and your L is here, let's say L1, yeah? I'm trying to explain to you this. So this Q is actually Fl. You get me? Okay. So with L naught, your Q naught is equal to Fl naught. When you have L1, your Q1 is equal to Fl1. And if your L1 is greater or equal to L naught, then this implies also Fl1 is greater or equal to L naught. But in this graph, it's very clear that it is greater. So by monotonicity, then we have this. But if we have greater only without equal sign, then it is strict monotonicity. But then what does it mean by but then what does it mean by quasi-concavity? By quasi-concavity, mathematically speaking, the input requirement set. So initially we have input transformed into output, isn't it? By quasi-concavity, input requirement set, which is given by this, I explain to you more about this bit and this bit later, yeah, is convex for all x element in the output positive output value or quantity. Okay, so mathematically speaking, it is like this, yeah. Basic maths say that if a function is quasi-concave, then you have the inverse of this function is convex set. Now that's it. So imagine, yeah, we initially talk about production function, which is continuous, increasing, and quasi-concave. So if production function is quasi-concave, and we know that production function is a function of, let's say, two inputs. I use y, yeah, here. Don't be confused with what I explained to you here. This is just explanation of this bit. But I'm talking about, you know, the concept of quasi-concavity. All right, let me repeat once again. If we have this production function, input produce output. Output y depends on input k and l. And we know that y as a function of k and l is a quasi-concave function. Now, if it is a quasi-concave function, then the inverse of this function is convex for all output. Okay, that means y is a function of k and l. Then K and L, let's say a function, let's say I'm just showing it in a very plain English. This is not correct. I just want you to understand the meaning of this inverse. K and L is a function of Q itself. You get what I mean? Now, if we relate it with what you have learned in your first year and also second year of your first degree or undergraduate level, this is what it means. Let me erase this first. I'm using small space to teach you. Okay. If we have production function which is increasing, continuous and quasi-concave, and then we have output here, we have, let's say, L here, and K for this, or whatever, L, yeah, for simplicity, yeah. But if we have the inverse, let's say L here, K here, then the inverse is convex. The quantity is fixed here. Then this one is isoquant. This one is production function. Can you see? This one is production function. This one is isoquant production function in the form of two inputs that produce the same amount of output. So this is the inverse of this, for instance. Conceptually, it's just a concept. Okay, conceptually, it means that. But mathematically, of course, I cannot just simply say that this one is inverse of this one is inverse of this. I'm trying to use whatever you have learned in your intermediate micro 1 and 2 just to explain to you this concept. Okay, but a formal way to explain this concept is not using this. It's not correct. I just want to use whatever you have learned so that you can visualize it. But again, the right way to explain this quasi-concave thing, inverse of quasi-concave production function is convex and whatnot. It's not like that. Okay. Just my main point is just to make sure you understand the concept. That's all. Okay. Click on. Use this first. So if we go back to this, by quasi-concavity, the input requirement set, the input requirement set which is here, is convex for all, X element in R plus. For all input element, or for all input as the member of the set of output. Sorry, for all output as the member of all output in one set. Call it real number positive here. Like I said to you, I'll explain to you this later, this one later, because it has something to do with the set. I'm just trying to explain to you the production function here first. Okay, so the next one is we want to look at the production possibility set below. So now we want to link the firm's production function with the firm possibility set. And the firm's possibility set can be written as this. Okay, so here, let me change the thickness of my pen. So here, capital Y is actually the output. Okay, and the output here consists of bundles of made from bundles of inputs. Let's say we have bundle Y, bundle X, and these are the element in the input that we have, the set of input. Okay, and also Y here, capital Y is a function of small letter y, and it has to be bigger or equal to X. Yeah. Now, when we talk about production possibility set, if you can recall back the utility function and utility set, they're preference sets. So we have preferences set, the set, and then we have preference, which is can be depicted in the form of utility curve. So in the chapter 1, we learn about the preferences set, its properties or axioms, and then we say that if we have utility function can also have the properties of preference set as well, as long as both of them have the same more or less assumptions and also properties. Okay, so same goes to production possibility set and also production function. Okay, now if we have production possibility set that conform with these characteristic, continuous, increasing, and quasi-concave production function. Okay, so if the production possibility set Y has these three, therefore production function also can have these three as well. Now, when we look at the quasi-concave, and you already learned the concept of concavity in the previous topic or chapters. So let's say we have, two bundles here. So we have yx and then y prime and x prime. Both of them are the element in the output function or output set, production possibility set. Then if we multiply each of them by scalar, call it lambda, by a constant, call it lambda, using this multiplication, this is the way we check the convexity mathematically, element in Y for all lambda. Okay, now of course this looks so difficult to understand. Let me show you in the form of a simple way. So this is just a revision of convexity, because in topic number 1 I also already mentioned to you the convexity concept. So let's say we have here output function as a function of two inputs for simplicity, x1 and x2. And then we show it in the simplest form, because this simplest form is the thing that we can visualize using two-dimension graph, and also the simplest form is the thing that you have seen before. So this is production function, or better known as isoquant, remember? Alright, so we have x1 and x2 here. So x1 here. Alright, now if we take two arbitrary factor or input bundles here. So let's say the first arbitrary input bundle is this, call it point A, and then another point B. So point A we have, let's say, x1, y1, sorry, x1, x2. I'm just making out. Don't be confused with input x1, input x2. x1, x2 that I'm labeling here for point A is just, how many x1, how many x2. And then we have another bundle here. How many x1? y1. How many x2? y2. You get me? Okay. So then, because we have these 2 points, if we join these 2 points, any point between A and B here, we call it lines because they are connected. Okay, any points along between A and B here, then we combine them, it become a line. This line we call it lines, let's say line Z for instance. So any bundles of input 1 and input 2, x1 and x2, within this line between A and B, within this line Z, okay, is preferred to bundle A and B. Okay, so in this case, let's say I use different color. Let's say I pick one point here along line Z, then I have another different bundle, call it Z1 here, Z2 here. So how many x1? Z1. How many x2? Z2. Input here, I'm talking about input, not talking about good 1, good 2 like in the utility function story. So here we can see that fz1, z2 is preferred or equal to, bundle x1, x2. Okay, so this one is also preferred to bundle B. Sorry, I forgot to put F here. So F Z1, Z2 is also equal or preferred to, at least it's preferred to x1, x2. Sorry, y1, y2 also. Okay, so you look at the sign that I put, I use this, at least it's preferred to. So if function of z1, z2 input production function is at least as preferred as production function of bundle x1, x2 for all bundles z1, z2 along this line, line z, okay, along this line, okay. Then what can we say here? The technology is convex. So if we can recall back, indifference curve and also look like this, isn't it? Now, this is at least as preferred too. Therefore, we call it convex. But if we delete this sign, equal sign here, then we call it strictly convex. So when we have a strictly convex function here, production, so they're strictly above the isoquant, basically anything, any bundle strictly above the isoquant, because this is the isoquant. Let me redraw it again so that it doesn't look like this. This is isoquant. This is point A, point B. One isoquant. And you can also have another isoquant and whatnot here. I'm just taking this isoquant. So if we have a line here, when we say strictly convex, so we're talking about strictly above the isoquant, okay, strictly above. Then we can have fx1, x2 is actually, sorry, the sign is wrong, is actually less than fz1, z2. Similarly, fz1, z2 is actually preferred to fy1, y2. That's convexity in the form of graph. But I want you to find a more mathematical way to explain it. Yeah. So here, if let's say we just make it a simplified version of production function in which we only have two factors or inputs of production in the model, monotonicity is very simple actually. Yeah? So I don't want to explain to you using proof of mathematics. You can always refer to the IC curve that you have learned or indifference curve that you have learned in chapter 1. Then you can apply it for monotonicity in the production possibility set and also production function. But in basic idea is that when we have monotonicity, if you have x1 and x2 here, okay, so this is x and then this is y. So this is actually y1 equal to fx1, isn't it? And then we have this y2 equal to fx2. So this is monotonicity. Okay, so if you have x2 greater than x1, this implies y2 greater than y1. But in the case of production function, it has to be something like this, yeah. So this is what this is monotonicity also. So x1, okay, less than x2, and then from here it goes down here, and then it doesn't increase like that. You get what I mean? So if it keeps, going like that, it is monotone. But if it is like this, conceptually, it is not monotonic. It oscillates. It's unstable. You get me? So that's a basic idea about monotonicity. In the form of mathematics, I want you to find it yourself, because this kind of thing I have explained to you in topic 1 or chapter 1. It's just the same. It's just that this time, like I said earlier, it's about production function instead of utility function. Now, when we have this, so let's say we have two functions. Guess I want to talk more about this concept. Yeah, the one that I'm explaining here is much simpler compared to the one in the textbook, because the one in the textbook, what the writer did was, the writer explained the concept of production possibility set first, and within the production possibility set, we can have many different types of isoquant or production function. That's what it means. So, but here what I'm doing is, I explain to you the production function first, because this is related to your undergraduate studies so that you can visualize it. But then I explain to you about the concept of production possibility set with its axioms or also properties. And then not very long, because my concern here is about production function instead. Okay, and then after that, I say to you, if we have continuous increasing and quasi-concave production function, then that means, okay, the production possibility set in within which production function is, within that set is also having the same axioms or properties. Okay, so let's say we have two factors of production. Let's say x1 and x2, yeah. But in reality, we don't only need two factor of production or inputs, because just imagine if you want to produce, let's say, a pair of shoes, you need labor, you need sewing machine, you need raw materials, and many more in it. All right, but in a simplified world, then I use two inputs here. Now, if we have two factor productions, and in this model, production model, then we can say that the production technology is strictly monotonic and convex, okay, such that x1 is a function of x2. So if you recall back, if we have isoquant, we have x2 here, x1 here, inputs here, and then we have isoquant that give you the same amount of quantity of output, let's say 10 pairs of shoes. Regardless any point here, bundle here, it gives you 10. Okay. Now this is just one type of production function, but the whole thing here is the set. You get what I mean? In the set, you can have many production functions because we can have many preferences. Okay, now let's go back to our objective here. As you can see, x1 is negatively related to x2, isn't it? So we have negative relationship. Why? Because in order for you to use more x2, you have to reduce x1 so that you can always produce the same amount of output for the same isoquant here. That's the concept of isoquant. So this is our model, production model. So imagine that, again I repeat, given a two-factor production model, the production technology that we have here is strictly monotonic and convex when, x1 is a function of x2, like I write here, I already wrote it, is the equation given for this isoquant. Then the implication is what? The results is what? So we have the results. G here, this function here is strictly decreasing. As you can see, isoquant is strictly decreasing. G here is strictly convex. Okay, if you put any point here, let me redraw it again. Yeah, x1, x2. You put here, you draw a line, the line is above the curve. You draw here, connect it, the line is above the curve. It's not clear, I show you. You put here, the line that you draw here is above the curve. You put here also above the curve. You get what I mean? So strictly convex. If G is, and also if G is smooth, then if this function, yeah, if G, this is called G function. Gx2 go to x1, because x1 is here, x2 is here. So if G is smooth, then if we take the first derivative of G, then we get negative, isn't it? Because downward sloping. We take the second derivative, it becomes positive. Why? Because this one shows convexity for all x, for all inputs. So when we have all of this, again I repeat, if you have this production technology, and when production technology is strictly monotonic and convex, then the implication is G, this production technology is strictly decreasing, number one. Second, it is strictly convex. Like I said here, you draw a line, it's always above the curve. And if G is smooth, then the first derivative of this curve, which is G prime, is negative, downsloping. And the second derivative here is greater or equal to 0. I put greater or equal to 0 for all input here. Then what can we say here is that this production function is well behaved. Okay, all right. And then lastly, the characteristic is that it must also be closed. If it is not closed, it's not easy for us to find the solution. Yeah, then we need to talk about the corner solution, Kuntaka and whatnot. Okay, so that's the idea of production possibility set. The basic main thing is that regardless whether you're talking about production possibility set or consumption possibility set, in the production possibility set like this, you can have many isoquants preferences, yeah. But then when we talk about isoquant or production function. If you pick one, let's say I use one different color here. So this is production function, okay, and in this production function here, it is convex following this. Okay, now let's go back to the simple understanding of theory of firms. For any kind of firms, when they involve in any business sector, the main point of engaging in business sector is to do business, to earn more revenue, to maximize profit so that they earn more income, isn't it? So now what we can do is that we want to show you, I want to show you how to maximize profit for the firm. Now, recall back, if we talk about consumer theory, consumers wants to maximize his own satisfaction by consuming goods and services. We change the story here to the firm. Firm wants to maximize profit by utilizing inputs into his production technology to produce output and then sell it in the market. You get what I mean? Both of them, although they are two different types of parties, but they have the main objective is to maximize their own satisfaction. To the producer, maximizing his own satisfaction means maximizing profit. Okay? Now, when we talk about profit here, you look at this equation. Of course, these equations here, I'm sure most of you have seen it before. Of course, we don't use the same alphabet when you did it for your first degree or undergraduate level, but of the same thing anyway. If you look here, let me change the italic form here, it's wrong. Okay, if you look here, the idea about this is to find how many quantity of output should be produced, how many, what is the price should be charged in the market, if it is not given, if it is determined in the market or whatnot, so that we know how to maximize profit. That's the idea, yeah? Okay, so let's say we have output price. Output in this case is producing, shoes. Price is P. And input prices. Now, when we want to produce shoes, we need inputs. Input, of course, I don't know how to make shoes by myself, but I want to have a factory of shoes. Therefore, I need to hire labor. Okay, so I need to have labor. I need to have sewing machine. So this is my capital. I need to have needles, threads, and whatnot. Now, all of these are not free. Labor, I need to pay wages. Sewing machine is a capital. I need to pay some amount of, payment when I buy a sewing machine, needles and whatnot, raw materials, leather and whatnot. So here, W is actually the vector of input prices. When I say the vector, it's not just one input. So because we have many inputs here, when we list down, it becomes a vector. So W1, W2 until a K input. Okay. Now the price here is the price of output. We don't give the product that we produce, in this case shoes, for free. So you can see clearly the price is not zero. And we don't give negative price. You know what does it mean by negative price? Negative price is actually when you produce output, you sell it, instead of you receiving money, you give money to the customer. You get what I mean here? At the same time, you give the product that you have produced and you want to sell. So here, look at the requirement of prices of input, where WK, K here refer to input number 1. Input number 2, usually we use WI, isn't it, I? But this time, just to differentiate between production theory and also consumer theory, we use K. So input 1, input 2, input 3 until input capital K. And you can see the prices of the price of each input is non-negative and non-zero. That means all of these labors are not free. All of these raw materials are not free. You want to produce shoes, you want to do business, you have to pay for the input, okay? Then that means the cost is not zero if you start to produce something. For all K, and therefore the profit is given by this function. Now, let me erase the miss first, then I highlight and show you which one is the profit function. So in general, the profit function, if you can recall back, you're studying the principle or intermediate when you did your undergraduate or first degree, you have profit equivalent to total revenue minus total cost. Now in this case, this one is profit, then you see minus sign here, then that means anything before minus sign here must be total revenue, and here is total cost. Okay, regardless whether they were talking about fixed cost and whatnot, like sewing machine itself is a fixed cost, isn't it? So you can see here price times output. Remember, Fy in the previous slide is actually output. This one, yeah? Okay. So price times quantity of output, quantity of product, then we have total revenue. And then minus. So minus must be, after minus, it must be total cost. So total cost is the price of input. The vectors of the price of input multiply the vectors of the input itself. Small letter y is the input. So your vector of input may consist of labor, okay, raw materials, sewing machine, blah, blah, blah. So this is vector of input. Then you have W here, vector of prices of input, labor, how much is it the payment per hour, raw material per kilo, and whatnot. Okay, so this is the profit function for any input in which is positive input. All right, this is positive input up to k number of input, and where W times Y is actually the summation of the total cost for each of the input. Okay, so you see WK, YK. So if you have summation of WK, YK, that means it is actually the price of input 1 multiplied by how many input 1 plus the price of input 2 multiplied by how many of input 2. And then if we have k up to 3, the price of input number 3 multiplied by input how many of input. So here the profit maximizing, this one can be rewritten as this as well. They are of the same thing. Now if you look here, I told you earlier that y is actually an input vector. Okay, y is actually an input vector that consists a number of inputs. If we have 3 inputs, land, labor, raw materials, then y vector here consists of, let's say, in the form of metric, number 1, number 2, number 3. That's it. Okay, now, so we have y. So y is the thing that we want to find. We want to find what is the value of, what's the quantity of input, call it y. Okay, when we have price of product and also price of input given. Because we need to find this quantity equal to what, so that we know that this quantity is maximizing profit. Now, how to find this quantity that can always make sure that our profit is maximized? Then we have to do, mathematically speaking, first order condition as usual, yeah? Okay, so like I said earlier, profit function consists of total revenue minus total cost. In particular, total revenue is price times output, which is Fy, minus total cost, which is the prices of input times input itself. So here, if we try to detail out the profit function, as you can see here, profit function depends on a price of output and also prices of input. And it is identical to total revenue, in which price times output. Output refers to Fy because Y itself is a function of price and price of product and also price of input. So we write it this way. Why? Because if we can recall back in the study of basic principle of microeconomics, the supply function, input price, input demand, Input demand refers to the quantity of input we want to hire in our production process. Depends on what? Depends on the price of product and also price of input. Now, look at this one because this one is easier to understand. Why input demand by the firm depends on price of input? Of course, it's law of demand. Okay, input prices, the price of input itself, of course, directly affect the input demand from the firm. The firm, logically speaking, would prefer to have cheaper price of input they want to use in the production process. Why? Cheaper price means cheaper total cost, isn't it? What about the price of product? Why it has something to do with the input demand? I can only start to demand more input if I know that the price of product that I want to sell is getting relatively expensive than before, because this give me a signal saying that, you know, total revenue consists of price times quantity of product itself. So if this one increases, putting other things constant, then total revenue increases, isn't it? So that's the determinants that you have learned in the first year. So here, second bit after the minus sign is total cost. Number of input, okay, for each input multiplied by the input price. Alright, so this is the production function that we have. Now, how to find the first order condition? Of course, I have shown you in this, slide here, but to come up with the detail. So, let's say I rewrite again the profit function here. Let me rewrite it here first. So our profit function is a function of price of product and also the price of input or factor production is equal to total revenue. In particular, total revenue is price times output, and output depends on input depends on price of product and also price of input itself. Okay, and then minus total cost. Total cost is how many input we want to hire multiplied by the price of input. Okay, and we know that the input here depends on the price of product and also the price of input itself. This one is multiplier. So to maximize profit, we need to find what we call first order condition. How to find the first order condition? Differentiate profit function in this case, okay, with respect to quantity of input. So here it's going to be price is a constant, leave it there, delta F over delta Y, okay, and then delta Y here is Y here itself is 1, okay. Use chain rule here, yeah, this one I'm using chain rule of differentiation, minus Y is here, W is here, okay, so W is our constant, Y we differentiate becomes 1, isn't it? Inside here, Y differentiate becomes 1, that's why you can see 1 here. First order condition means differentiation here must be equal to 0, because that means marginal profit is 0. When marginal profit is 0, here the slope is 0. Let's say this is a profit function, the slope is 0. At 0 point here, you can see maximum profit. Okay, I hope this is clear. Now, when you rearrange it, then you can get W over P equals to delta F over delta Y. And this is for one input. Yeah? Let's say input K. Okay. For instance. So, you want to do for another input, second one, do the same thing until the last input, call it capital K. So can you see it's just the same as, utility function. In utility function, you have many goods. To maximize utility, you differentiate each of the utility function with respect to each of the good, equate to 0, and then rearrange, you get something more or less like, MRS equal to what and what. So same thing to production function, you differentiate profit function with respect to one input, let's say input 1. This time I write K instead of 1, because I just want to show you one example. And then differentiate it, you get 0, equate it, then you get this. You have the second input, you do the same, so on and so forth. So we have a lot of input, a lot of list here. Okay, so here, what we can say is that, you look here, the marginal product of one input is actually equivalent to the price of input itself. Now, this is not something new because you have learned this concept in principal and also intermediate level of your economics at the undergraduate or first degree level. So here, this signifies what? All of this is actually signifying, not this one here, because if we do more, because when we talk, not this one, I'm sorry, this is a mistake, not this one. I'm planning to explain another term actually. So if you can recall back, isoquant, let's say we have two inputs, x2 and x1, and then we have isoquant that look like this. Isoquant says that all the combination of two inputs along this isoquant give you the same amount of output, let's say 10 pairs of shoes. Okay, let's say in a simplified world where we only have two factors of production, so that you can understand the concept. So here, when we want to produce the same amount of shoes, currently we are here, so x1, x2, then you move here, x1 prime, x2 prime. When you move from point here to point here, make sure you still produce not more, not less than 10 shoes. But you can see here, at this point A, you have a lot of x2, less x1. But as you move to point B here, the bundle changes, where at B, you have a lot of x1, less than but less x2. But then by reducing, x2, in order to get more x1 input in the production process, you can maintain the same amount of Q here, which is 10, the same amount of product here. Okay, now because of that, this kind of movement is actually the slope. Yeah, there's a way to calculate it, and then this slope is what we call marginal rate of transformation. Okay, marginal rate of transformation for two different input, in this case input 1 and 2. Now, to put it in a general explanation, this is what I mean just now. So if we have assume that production function can be differentiated so that we can find first order condition, mathematically speaking, yeah, so that what it means by this term. Then we found this have been shown earlier. Also, I've shown you in the form of graph just now like this, but mathematically speaking, the MRTS is actually this. It is actually how much is the change in output due to the change in the change in output due to the change in, let's say, input x1, for instance. And here, how much is the change in output due to the change in input x2, for instance. Let's say x1 here is labor, x2 here is, let's say, sewing machine. How many quantity you need to reduce when you reduce the amount of labor in order to get more amount of sewing machine? How many quantity has to be reduced that can, by labor in order to get additional quantity produced by additional sewing machine for all input, labor and sewing machine. So that is MRTS. So this MRTS actually give you one meaning, that is the slope of the isoquant itself in this kind of manner. Okay, now, so at the optimum level, let me redraw again. If we have isoquant x2, x1 here, this is the cost function, this is isoquant. At this point, then you can see the ratio of the price, the cost, the marginal cost, is actually equal to MRTS, the slope of isoquant. Okay, so let's say one observes, an individual observes the profit of the firm and prices. Can we deduce that, the production function and the optimal production? Is it possible to do that? Yes, of course. So let me rephrase again the question here. What it says is that, just imagine, can we find the best what? A, the best quantity of input to maximize profit, B, and find the production behavior that can maximize profit if we know the profit of the firm, what's the value of the profit, and if we also know the prices of the input and the price of the product only, can we find the quantity of production which is bringing us to the maximum level of profit. Is it possible? Yes, it is possible. We use envelope theorem. Then we can have what we call Hotelling lemma. If you can understand more about it, it's just the symmetry of consumer behavior, but this time we have production behavior, but the name is a bit different in terms of lemma and whatnot. If you can recall back in consumer theory, you have Slutsky equation, you have Marshallian demand and whatnot. But in this case, we have Hotelling lemma to get what we want here. Okay? Now, how can we use Hotelling lemma in our analysis here? Now, let me rewrite again the profit function. So, the profit function, as we can see, is a function of price of output and also price of input, in which we have total revenue minus total cost. And total revenue is price times output quantity. Okay, and we also can have minus total cost here, which is output quantity multiplied by output price. So all of these are the vectors. Now, before I proceed with Hotelling lemma, if you see the profit function here is a function of price of output and also price of inputs. Okay, so this kind of profit function is what we call indirect profit function, because the indirect profit function that we have here is depending on prices of output and also price of output and also prices of input instead. Okay, so let's crack on. Now, when we want to have Hotelling lemma, what we need to do is that we need to differentiate this profit function with respect to price. So when we differentiate it with respect to price, you look here, dp over p Greek letter over p Latin letter. You look at this because we can see p here. And if you look at this and this, there are p inside, y here, isn't it? Because input depends on price and price of output and also price of input itself. But this is not our concern. When we differentiate profit with respect to price of output, what we get here is that this one, P here becomes 1, and then this is a constant, isn't it? Okay, and then because we don't see P here except within here, endogeneity, but we are not concerned about endogeneity this time, then we have this. Now, what we have done here is that we apply envelope theorem to perform Hotelling lemma for the first example. If you can recall back the Hotelling lemma, not the Hotelling lemma, but the envelope theorem itself, we also applied envelope theorem in the consumer theory previous chapters to derive Hicksian demand in the case of, utility theory. So here, same thing, but we apply it for profit. And in particular, this is indirect profit function. Okay? So usually profit, if we just have a simple one, profit is actually price times output, isn't it? And then minus output times price of input, isn't it? So differentiate it with respect to P, you get Fy. And Fy is this. Okay? So you can see here, the change in profit is due to the change in price of output. And the results here is exactly the same as the quantity of output produced at that particular point. Okay, now what is this actually? As you can see, it is positive. So whenever the price of output increases, profit increases. Okay, and then what we see here is that the answer is the quantity of output. So here, what we can say, it has something to do with output supply. Output supply starts to increase, okay, if price of output increases, because like I said earlier, increasing the price of output means increasing total revenue for this firm. That's why they have tendency, the firm has tendency to produce even more. So that's why the value is positive here. Now, Hotelling lemma can also be applied, okay, if we try to derive the profit function here with respect to input prices. Now, when we derive it with respect to input prices, what do we get? The negative value of quantity of input that the firm will hire. So this is very simple. As input prices increases, you can see that the profit decreases by the same amount of output produced. Okay, so it has negative relationship here. So for instance, if this is about labor demand, the K here is labor, so W here is wages, isn't it? Okay, so this is the change in profit due to the change in input prices, and it gives you this. So basically here, what is this? This is demand for input by this firm. So you can see clearly the profit function here is decreasing in WK, the price of input K, and increasing in the price of output, isn't it? Okay, now, so here again, I would like to repeat once again, yeah. Here, when we try to derive answer using Hotelling lemma, we are basically applying envelope theorem. Again, this is analogous to the concept of consumer theory that we have previously when we try to derive Hicksian demand in the consumer utility theory. Alright? Okay. Now, so here we want to move to the next thing, the convexity. Okay, now you look here. Then we want to talk about the convexity of a function. Like I said earlier, production set is convex. Therefore, the production function correspond to this kind of production set is also convex. So if we have a function, let's say G, and G here is production function, for instance. Input here, the number of input here is being mapped into one output using this function. And it becomes a convex function if what? If this property is fulfilled. Now this property has been taught to you when I taught you consumer theory for utility function, remember? When we talk about convexity of preference set, utility function, and whatnot. So I hope you can find the similar explanation in terms of proof. Okay, I'm not going to show it again here because it's a repetitive thing. Now, let's look at proposition 2. So, if we have profit function, which is this, okay, profit function is convex in P and also W. Okay, profit function is convex in P and also W. So, the proof here, I want you to try it out. And from this proof, if we use Hotelling lemma, and also by the convexity of profit function, because we say that in proposition 2 profit function is convex in P and W, so we use this convexity concept or theorem and also Hotelling's lemma, then we can derive this. Now let me derive it one by one here so that you know the step. Okay, so we know that the profit function is given by P times Fy, isn't it? Okay, now I don't want to write PW here, yeah? And minus Y multiplied by W, isn't it, the price of input? So previously, when we differentiate profit with respect to price, what we get here is that the output is solved at that particular price. Okay, now if you look here, we differentiate this again, so df over dp. Okay, and then here differentiate it again, what do we get? So we must get the value which is positive or at least 0. Okay, so why can we differentiate Fy with respect to why can we differentiate Fy here, the production function, with respect to price? Because if you go back to the previous, Y is a function of P and W, that's why we can differentiate it again. So when we differentiate it again here, the profit function again, then we can see that it is the relationship between price and also output. What's the relationship? The relationship is positive. So look at A. If the price of an output increases, which is this, yeah, then the supply increases. How do we know the supply increases? Because the output here is increases by, more than 0 or at least 0. then the supply increases. What law of economics is this? This is nothing else but law of supply. Remember, quantity supply and price. All right? And recall back for the profit function, if we differentiate it with respect to the price of input, then we get minus y, isn't it? So if we differentiate it again, second time, then we are basically differentiating the input that we have earlier with respect to price of input itself. So recall back here, we have this answer, remember? Okay, let me change the color of the pen. We have this answer, remember? And we see the minus sign. We bring the minus sign here. We differentiate this thing with respect to price. So I bring the minus sign from left to right. And then differentiate y with respect to p. So when we have this, we still have, less than 0. The relationship between, the price here, not the price, sorry, there's a mistake there. Not the price, but the price of input and not just P. The price of input here, the change in the price of input leads to the reduction in input. Okay, so look at B. If the price of an input increases, then the demand for the input decreases. Who demands input? Firm. Why firm demands input? Because firm wants to use input to in the production process to produce goods and services. Now, because the input here is not free, so the firm has to purchase. So when the price of input increases, of course the firm won't be able to buy more input and produce more. So this is what? This is law of demand between price and the quantity of input itself. So this one is law of demand. Alright, I hope this is very clear for you. So if we have production function here in which we have Fy, but if we specify further F as a function of input, in which input is a function of price of output and also price of input itself, then this kind of thing is actually the optimal output under any output price P, okay, and also the W, given W itself. And here, what we can do here is that you can, if you can recall back, we did, Hotelling lemma in which we differentiate profit function with respect to price, and we receive this answer, isn't it? Okay. Now, but if we reverse it, in other words, mathematically speaking, we integrate it like this, then we can obtain what we call profit function. This one, okay, we integrate it, then we get the profit function. This one, we integrate it, then we get profit function like this. Okay, now this is just a basic integration here. Up to what point? From 0 up to P price. Okay, this is a very basic differentiation here. For instance, if you have 5 as a constant, so 5x, isn't it? So this is the integration, yeah? Y prime, this one. So y prime integrate, you get this, of course, plus constant. But in this case, we are not concerned about constant. So the same thing with this, yes, the basic integration. So here, if we try to visualize it, but here I'm not going to draw the graph, yeah, because the graph is a bit complicated with this, abstract thing. If you have a profit function, okay, that has been integrated using this concept, then if it is I'm trying to visualize it. So let's say this is a profit function. I'm just making up, yeah. This is a profit function. So if we have quantity here up to this point, then profit is here, isn't it? P1, Q1. So from 0 to this is our, quantity and profit. But if we have production function, let's say isoquant like this, and then we have the price because we need another one here, then it should be area under the production function and also the price axis itself. That's why I cannot visualize it here because it is very abstract also. Because remember, like I said earlier, profit function here is indirect profit function because we represent it in the form of endogeneity of price and of output and also price of input. That's why to visualize it, it's a bit difficult. We need computer to do this. Okay, now, so we are done with this, but then of course later I'll show you, examples here, because if I just explain to you from the beginning like this, from here, 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 and everything, based on theory, of course you don't understand that much unless if you're very good in, mathematical notation and also the conceptual, thing for theoretical part of economics. But we want to move to cost minimization problem first before, anything else. Then after that, I'll explain to you using a simple example. Okay. Now, what we did previously, we maximized profit, isn't it? But now we can also have cost minimization. So what is the cost minimization concept in the study of production theory here? The cost minimization problem. So here, what we can say is that, let's say for each quantity of output, we call it Q, small letter Q here. We need to find the least costly input combination that yield Q. In other words, we want to find how many output we need to produce, the quantity of output which is Q, that can give us the cheapest cost of production. When we can produce that amount of quantity of output with the cheapest cost of production, if you can recall back your principle of microeconomics that you learned in first degree, then that means we have productive efficiency. Okay, so here, minimize cost. The cost that we have here is actually total cost, in which vector of input prices, which is W, multiplied by vector of input, which is Y. Okay, and it has to be subject to Q or output equals to production function. So if you solve this, you need to find the first order condition and whatnot, Lagrangian, do the Lagrangian and whatnot. Then you can find the solution, and the solution here, we name it, we just name it. You can name it whatever as long as it is a function of input prices and also quantity of output. And this is what we call conditional factor demand function. And then the cost function that we have, after we solve this problem, the cost function that we're gonna obtain is a function of input price and also a vector of input prices and also quantity of output, and this is what we call cost function. So here, Y here is the how many input we need to produce. So W times Z, we get the total cost. So you see this one and this here. Okay, Z here is completely similar to Haxian demand function in our consumer theory in chapter 1. And the cost here, okay, is actually the same as expenditure function that we have in utility consumer theory. Okay, now let me give you one example so that you can be clear about it. Let's say we have two inputs, labor and capital. So we want to minimize cost. Now let me write it. Minimize cost, because we have labor. Labor, the price is wage, plus capital, the price is rent, isn't it? Then subject to production function denoted as Q as a function of K and L, can you see? Okay, such that L is non-negative value and K is also non-negative value. And here minimize, the argument is L and K. Okay, so now if we have C, okay, it's actually any cost level, then the isocost line can be rewritten as this. C equals to WL plus RK. Okay, and it contains of all input. In this case, we only have two inputs, and in this case, you can see the isocost here is combinations of K and L, which costs C amount of ringgit or dollar and whatnot. The total cost is C, yeah, that's what I mean. So the equation here can be depicted in the form of graph, but before I depict it in the form of graph, I can also rearrange it so that we can have K as a function of L. So if you rearrange it, I hope you get it because this is simple maths. So you have K equal to total cost divided by rent minus W divided by R times L. So if you put it in the form of graph, becomes easier because we only have two inputs here. I use simple example. K here, L here. So you see this, you know that it's a straight line because if you differentiate K with respect to, let's say, L, for instance, you're going to get this answer. And this answer both positive meets negative, then it's this. So it is downsloping. So if you differentiate it once again, take the second derivative, what you get here is that you don't see R, so it becomes 0. That means you know that this curve is a straight line. The second derivative is 0. Then you have this. Now, what about the value here? The value here is the value of K when L is 0. K becomes C over R when L is 0, isn't it? You can substitute it back into this. You can find that it is here C over R. What about here? If it is here, then it becomes C over W. That means K is 0, you rearrange it, you get C over W. Okay, now after that, this cost problem, this cost analysis, if you have isoquant, then you can have something like this. So this is isoquant, Q equals to F, KL, and then this is our isocost, C equals to WL plus RK, and then this slope is actually minus W over R. Now at this point, call it point A, the slope of isocost equal to the slope of isoquant. And the slope of isocost, we know it already, minus W over R. It is minus because it is downsloping. Slope of isoquant is MRTS. This is the simplest way to explain the cost minimization problem using two inputs. Okay, now, but then, if I were to put it in the form of general idea, I mean the solutions, yeah? The solutions after we do the first order condition. By now, you should know what does it mean by the first order condition. You put Lagrangian, you take, the first derivative of cost function with respect to input, then you equate it to 0. And then we can have the first solution, we call it conditional factor demand. And this conditional factor demand is L as a function of output, wage, and interest rate. The same goes to K as a function of output, wage, and interest rate. Oh, initially when I talk about capital, yeah, let's go back to this. Where is it? Is it here now? When I talk about this, I said R is rent. It's not rent, yeah, it's interest rate. There's a mistake there. Okay, let's go back to this. And the second thing is total cost function. Okay, this total cost function that we obtain from this cost minimization problem, it provides minimum cost of producing output Q at price of W and R. So we have cost as a function of Q, W, and R, in which W, optimal level of L, plus R, optimal level of capital. Now, when I say it is an optimal level, it is here after you do the first order condition of cost minimizing problem and rearrange it. So here, because L star is this, after we do the calculation, so L, Q, W, R, isn't it? R, here. K star is K, Q, WR. Sorry. Okay, right. Now, and the next thing that is also very important, average total cost. Now, average total cost is total cost divided by quantity of output. The total cost is this, okay, the one that we found after cost minimization problem, divide by quantity. What about marginal cost? Marginal cost is very simple. Differentiate the total cost at optimal level with respect to Q as well. All right. Now, the next thing, back to the optimal production here because this is very important. And because we're talking about the cost function, and if you go back to the optimal level of production, profit maximization, cost minimization, and actually when we talk about the cost function here, the problem of the firm simplifies remarkably. We just need to find optimal level of output, that's it. Okay, so for instance, let's go back to the profit function here. Given P and W in the market, if we have a firm, the firm's objective is to solve the profit maximization problem. So because this is total revenue, this is total cost, so obviously the whole thing here is what we call a profit function, isn't it? So if you differentiate the profit function, okay, let me rewrite again the profit function here. P equal to, this is Greek letter P equals to Latin letter P times Q minus CWQ. Okay, so differentiate profit function with respect to Q because just find the optimal level of output. So you differentiate it with respect to Q because that's your objective. Find the optimal level of output. Output here refers to Q. Okay, then we get P times Q, P, isn't it? Because if you differentiate it using simple differentiation, that's what you get, minus delta C over delta Q. C is a function of W and Q. And then don't forget, because this is a first order condition, we want to maximize, equates it to 0. Profit maximization. So if you rearrange it, what you get here is P equals to delta C over delta Q, which is this one. So what is this, class? If you look at this, it is a change in cost due to the change in quantity of output. Okay, one additional unit increase in quantity of output, there is an additional increase in a cost. So this one is actually what we call marginal cost. Marginal cost is actually equals to the price level. If you can recall back in your study, P equals to MC, okay, in your first year undergraduate or first degree, P equal to MC happens in the perfect or pure competitive market, pure competitive firm in a competitive market. So here, we can see clearly that at the firm's optimum production, the marginal cost is actually equals to the price. So you can see here, let's recall back your first year study. When price is equal to MC, now this is MC, this is the demand or price, isn't it? And then this is the minimum. Price can also here. So MC here, my main point here, it's the marginal cost curve, which is the delta C over delta Q, defines the firm inverse supply function. Why? Okay, let me redraw it again here. For MC, and then this is AVC. Anything above minimum AVC in a pure competitive firm, the firm will produce. But if it is below, the firm won't produce because the firm cannot cover the cost. Okay, so here, any point along MC above minimum AVC is what we call supply curve or supply function. That's what you learn in the undergraduate level. So because of this condition, plus what you have in your first degree or undergraduate level, then delta C over delta Q actually can be deliberately defined as the firm's inverse supply function. This one. Alright, so I hope this is clear. You're going to see a lot of exercises later. Here, I'm explaining to you about the concept first. Okay, let's recall back. We know that you look at this equation, yeah. This bit is actually profit function, and this bit is actually the integration of the FOC that we did earlier. So let me rewrite again. Profit is actually P times Q minus W times Y. But because if you can recall back, this one is total cost, because after the cost minimization problem, we get the cost function that looks like this. So I can substitute it back here. So P Greek letter equals to P Latin letter times Q minus C as a function of W and Q. You get me? So this is what I'm talking about. Now from here, if you can recall back in the previous slide, we did find the first order condition in which we differentiate profit function with respect to output, okay? Because of this statement, look at this. The problem of the firm simplifies remarkably because we just need to find optimal level of output. Now, let's go back to this. So when we differentiate it, we have P minus delta C over delta Q, isn't it? And then equates it to 0. Okay, now, if you take this, you integrate it, the whole thing here, then you go back, you reverse back to the profit function, which is this, isn't it? That's what it means. So basically, if we try to put it in the form of graph, the area between P and the inverse supply curve reflects the firm's profit, which is true. So if we have this is our MC, and this is our, let's say, ATC, and then this is our price between this, below the, inverse supply function. The area between P and inverse supply function, between this is P, the inverse supply function is this, and then it gives you profit actually, yeah? Okay, now, there is another thing, another concept, another very interesting concept that we need to recognize when we talk about theory of production, when we try to maximize profit, or we try to, on the other hand, we try another different way, cost minimizing problem. Then we have the concept of what we call duality in the production function, like the same duality that we have in consumer theory. Before we proceed to the next slide of production theory, let me talk again about the duality in the production. Now, if you can recall back, we have the duality in the consumer theory, so same goes to duality in the production. So for the production, for any firm, we already know that each firm wants to maximize profit. So, but the limitation here is that in order to maximize profit, the firm must have, output produced, and at the same time the input used to produce output must be purchased. Therefore, there is a constraint. So here, if you look here, maximize output Fy, the production function, subject to the cost constraint, which is less or equal to the cost itself. Okay, the expenditure on the input must be less or equal to the total cost itself. So it has to be within the budget of the firm. But if we look at the duality problem, then it becomes cost minimization. Now, cost minimization is minimizing total expenditure on input subject to the given output, which is this. So the output is constant, but this time we adjust the expenditure. But here, the cost is constant, but we adjust the output. So these general equations are not usually useful on their own. Why? Because of this less or equal sign. So same, it's just the same thing like what we have for consumer theory. Okay, and so because these general equations are not usually useful on their own, therefore we need to reformulate both of them, so that they can be easier to analyze. So if we read this new product maximization, that say we have two inputs, so I would use two inputs here, maximize production function, which is as a function of K and L, and subject to the cost constraint. So total cost is this, break it equal sign, and total cost is equivalent to the total expenditure on capital plus total expenditure on labor, which is this side. Okay, so here what we see is that the maximum production given by the two factor of production, which is capital K and also labor L, that is subject to the budgetary constraint, which is equal to the sum of factor of production here. And if we want to talk about, specifically, it is actually equals to the sum of expenditure on capital and also on labor. Okay, now, and also on the other hand, if we look at the cost minimization, the duality problem, the newer equation for the dual problem is now noted as cost minimization problem, and in particular, it becomes this: minimizing, okay, C equal to RK plus WL subject to output function, okay, which is equivalent to Q. For instance, a constant Q. You see, we just need to change it to this so that it's easier to do the calculation algebraically. So since we only have two factor production considered, okay, so this kind of analysis can be put in the form of graph. Now, you look here for the product maximization. So we have labor here, we have capital here, and then we have the budgetary constraint, which is this, and this is basically ISO cost. Because you have two inputs, it's much easier to put it in the form of graph. Now, let me fix the ISO cost here. It should be a straight line instead. Okay, so here, if you look carefully, finding the optimal level of factor production cannot only be seen as a question of choosing the highest production isoquant tangent, but we are not only finding the highest isoquant, because at the same time, of course, we want to find the highest isoquant so that we can produce the highest level of output, but then we have constraint. Okay, so given isoquant line, okay, when maximum production is achieved, okay, then how do we do it? It's basically when the wrong drawing here. Let me redraw it again. So here again, yeah, because we have limitation that is isocost. So given isocost line, when maximizing production here, we are basically trying to make sure that our production reach this equilibrium in which isocost is a tangent to isoquant. So if we are here, well, then we try to reach the maximum isocost, but not here because it's not attainable, isn't it? So it's here because we have budgetary constraints, so call it point A. So that is the product maximization problem. But when it comes to duality, so given isocost line, when maximum production is the objective, but at the same time here when it is duality, okay, there is a question on of choosing the lowest cost function. Okay, so choosing the lowest cost function here, so let me draw it in the form of graph here. So we have L here, we have K here. Okay, now and we have the budget constraint. So if you have isocost here, it doesn't meet the the optimization because it's not within our budget. So we try to minimize cost. So try to find another isoquant, no? Then try to find another isoquant, which is this. So this is the cost minimization case. So that is the idea. So here we try to achieve the maximum isoquant, but then it has to be achievable in such a way that it is within our budget, which is here. So this highest isoquant is not attainable. On the other hand, when we have cost minimization, we're trying to produce and to achieve, isoquant given isocost, given the limitation. Okay, so we choose the lowest one, which is here, because there is no budget here. If we have budget here, of course, it's possible for us to choose here, but the lowest budget possible is this one. You get what I mean? So that's the idea between duality in the production, the connection between production maximization and cost minimization. In relation to the cost minimization, now I want to introduce to you another lemma other than Hotelling lemma, because this is very important as well. Yeah. So this is what we call Shepard lemma. Now, when we talk about Shepard lemma here, it is basically a derivation from envelope theorem, and I'm sure you already know the envelope theorem because you have heard it in chapter 1. So Shepard lemma is a derivative from envelope theorem, which states the change in a firm cost from a change in input price is actually proportional to the input demand by the firm. Mathematically speaking, formally, it is if you have cost function, cost is a function of input price and also quantity of output, yeah. Then what you do with this cost function is that you differentiate this cost function with respect to input price, and what you will receive here is actually output of certain input, which is a function of input price and also quantity. So what it's trying to say here is that if you talk about Shepard lemma, so the change in cost due to the change in input prices is actually the same as the amount of input demand. Okay, I give you a numerical example. So let's say we have one firm. Okay, let's say this firm has two output Y1, output Y2. Okay, so what he needs here is that he needs 10 Y1, he needs 4 Y2, so that with these two types of inputs, he can produce Q unit of output or product. Now, the cost for input 1 is, let's say, 1 quid. The cost of input 2, let's say, 1 quid as well. So in this case, then the total cost for this firm is what? Is actually cost as a function of input 1 and also input Y2, and in general W1 Y1 plus W2 Y2 in it. Now in this case, W1 is 1 quid, and Y1 is 10 quantity, W2 is also 1 quid, and quantity for input 2 is 4, Y2 is 4. So total here is 14. Now let's say the price of input 1, input Y1 increases. That means W1 increases. Okay, let's say increases to 2 quid. So what is the new total cost? The new total cost, let's say I put it C prime, Y1, Y2, is also with, W1 prime, Y1 plus W2, Y2. And in this case, so it becomes 2 quid instead of 1 times 10 plus 1 times 4. What do you get here? 24. Now, if you look here, look at the difference between these two costs. This is cost number 1, this is cost number 2. The difference is actually 24 minus 14. And this 24 minus 14 is actually equivalent to 10. And if you look at 10 here, it's exactly the same as the amount of input 1 needed in the production process. So this is what we mean by Shepard lemma. So if you differentiate a cost function with respect to input price, okay, then it is actually the same as the amount of input, okay, demanded at that particular level. In this case, W1, so we have Y1 here. Okay, so that's the idea of Shepard lemma. Alright, so let's crack on. So we want to look at the geometry of the cost, and this is very basic actually. This is just a repetition of what you have done in the principle. Let's say the firm has to invest, let's say, K positive value to operate in the market, and some costs do not affect the optimal production. Assume that, if we engage in the market, it's always profitable. So we don't miss a lot of costs, especially sunk costs. So let's say average cost of the firm from production Q unit of output is given by this. Okay, so here as you can see, average cost as a function of Q is actually sunk cost plus variable cost. Okay, and then this divided by Q just to get the average. So AC here is decreasing whenever the marginal cost is lower than AC. So this is very basic actually. I'll show you in the formal graph after this. And increasing when, marginal cost is higher than AC. So this means the curve cross at the minimum of AC. So this is just a repetition. Okay, so if you have cost here, and then you have quantity here, now this is marginal cost, and the way you draw average cost should look like this. You see what I mean? And you look at the minimum point of average cost is here. Whenever average cost is at minimum point and you want to put MC in the same graph, MC will only intersect with AC when AC is at its minimum. Okay, so you can see here I can divide it into two different segments. Now the first segment here you can see average cost, which is this. Let me use a different color. Yeah, average cost, which is this, is above MC. So you can see that average cost is declining. But in segment 2, average cost is below MC, isn't it? So this is average cost. This is MC. As you can see, if I pick Q2 quantity here, average cost is here, average cost 2, but MC2 is here. So you can see MC2 is greater than AC2. This is very basic, yeah? Then what you can see here is that average cost is increasing. So average cost is increasing whenever you are in the second segment. So look at the last point here. Unless the firm can operate at price P such that P equivalent to, differentiation of cost function with respect to output, which is greater or equal to AC, it does not enter the market. So what does it mean here is that, let me redraw again the curve. So if we have Q here, we have cost or money here. Then you have MC here, you have AC here. So if we have a price, okay, this is price equals to MC greater than AC. So if price is here, MC equal to AC, MC equal to P, because P here behave like marginal revenue, so MR equal to MC here. So AC is here at Q, let's say Q1, AC1 here, P1 here. As long as P1, okay, equals to MC at point A, but then it is greater than AC1. Okay, you get me? So it's Q here. How do I know this? Because first, when you draw it, MR equal to MC for the profit maximizing rule. How do I know MR equal to MC at point A? Because MR itself is price. So this is pure competitive actually, yeah. Then the firm will enter the market, make profit and whatnot. But just imagine if the price is here. So it hits MC here. It's obviously below the AC, isn't it? So you can't cover costs. If price is below AC, that means total revenue is below total cost, isn't it? So you can't cover the cost. So it does not enter the market. So for this, actually, it's very simple. You go to the pure competition, and then you learn about profit maximization, the optimal level, the rule, because price has to be equal to MC to maximize profit, and learn how it is decided. So there are a lot of, textbook on this topic for first degree or undergraduate level. Now let's emphasize some differences between consumer theory and also producer theory. If you look at the consumer theory in chapter 1, when we talk about utility function U, it only represents preferences, yeah, at least as good as. But usually utility satisfaction of a person or individual consumer, even in principle, even in reality, is very difficult to detect, very difficult to quantify, because it can represent multiple representations. I make you a simple example. For instance, if people ask you, would you like this food? Oh, I like it. But I'm not sure whether you are sincere or not when you say I like it, how much you like it, up to what point. You may rank it when people ask you, can you rank which one is, which one is the best for your appetite and whatnot. You may rank it, but still, the way you rank is, is very abstract. So that's why it's not easy to be observed in principle. But when we compare with production function, F for instance, yeah, it is a unique description of the technology, and in principle is observable. Why it is observable? Because if you have certain amount of capital K, let's say we have two inputs only in the production function. If you have certain amount of K, let's say 10, and you have certain amount of labor hours, let's say 200 hours. Now from this 10 capital and also 200 labor hours, in the factory, you put the effort like this, and then you can see the output, not in abstract form, in tangible form, okay? And another point here, not only ordinal but also cardinal differences have meaning under production function. Okay, for instance, concavity of production function F is also mattering. So here production function, if you order it, it gives certain meaning as well. If you have cardinal, also certain meaning, gives certain meaning as well. I'm not saying that utility function, when we put it in the form of order or cardinal, it doesn't give you any meaning, but the meaning is very abstract. So it's not very tangible to see and whatnot. If I tell you I'm very happy, how much is your happiness? This much. I show you, I show you my hand showing, a circle around me. I'm saying that I have highest level of satisfaction, but it's still very abstract. Okay, because if your achievement is small, for instance, according to other people, but you see that it's a big thing for you. So, the question of measurement is very abstract here. All right. Now, we need to move to examples so that you can understand better about producer theory. So here, I want to show you a very simple example of cost minimization problem. So let's say we have two inputs, Y1 and Y2. So W1 is the price of input Y1. W2 is the price of input Y2. And of course, a cost minimization here is subject to production technology or production function given by this. Okay? All right. Now, let's do it. So, and also we need to make sure that our input, both of them are positive, otherwise we cannot produce anything. If you don't, let's say Y1 is labor, Y2 is capital. If you don't have capital and labor, then you cannot produce anything. You get what I mean here? So that's what it means by greater or equal to 0. All right. Now, so here, before I proceed, then you must remember if it can be analogously compared with problem of expenditure minimization problem in your study of utility analysis in chapter 1 in consumer theory. Now, before I forget, I forgot to write this here. When we talk about Q, here we make it specific function. Let's say we have symmetric Cobb-Douglas function. Symmetric Cobb-Douglas function, which is given by y1 gamma to the power of gamma, y2 to the power of gamma. So we have symmetric, the power is the same here. Okay, but of course, this gamma is between 0 and 1. Okay, otherwise we don't have Cobb-Douglas function. Okay, what we need to do as usual, when we have cost minimization problem, because I told you that it's more or less similar to expenditure minimization problem in the utility analysis. So we need to construct a Lagrangian function. So Lagrangian function, okay, let's say it is L. L is equivalent to W1 Y1 plus W2 Y2 and plus, we put the scalar which is lambda, and then here Q minus Y1 to the power of gamma times Y2 to the power of gamma. So what we need to do next is to find the first order condition, because with a first order condition, then only we can minimize the cost. So our first order condition should be written as this. What you need to do is that you need to do a partial differentiation with respect to y1, y2, and also lambda. So we're going to have 3 different types of first order condition. Let's do it. So differentiate lambda function with respect to Lagrangian function with respect to output y1. Then we're going to obtain this w1 minus lambda y1 to the power of gamma minus 1 times y2 to the power of gamma, and then equate it to 0. So we have the partial differentiation. When you equate it to the 0, then it becomes a first order condition. Whenever we equate it to 0, this marginal analysis becomes, the value of marginal here, the change in Lagrangian function due to input y1 is 0. That means, the slope is 0. Slope is 0 only. You see slope is 0 like this or like this. It can be at the maximum point or minimum point here, but because we are talking about cost minimization, then we are talking about this bit. All right. Now, so this is the first one. I call it equation 1. Now, we do the second one, delta L over delta Y2. So you're going to have W2 and then lambda, Y1 to the power of gamma, Y2 to the power of gamma minus 1, equal to 0 as well. Then this is equation 2. And the last one here, delta L over delta lambda. Now here you get Q minus Y1 gamma, Y2 gamma equated to 0. And then this one is 3. Now from here we can simplify it even further. We can have Q equals to Y1 gamma, Y2 gamma. Okay, now if you look at expression 1 and 2 that we have obtained earlier, what we need to do here is that if you rearrange it, now I'm not going to show you one by one, yeah, but if you rearrange it, what you get here is W1 Y1 equals to W2 Y2. Why it happens like this? Because in this case, our Cobb-Douglas function here is power is symmetry, so we can obtain this. So let's call this one expression 4. Now, what we need to do next is that look at this. This is 3, this is 4. Now, let's call this one, after I simplify it, call it 5. Yeah? Q equal to Y1 gamma to the power of gamma, Y2 to the power of gamma as expression 5. Now, from 5 here, we need to do some, algebraic, calculation. So, from 5, like I said, I'm not going to show you the calculus here because it's simple. So, we can have this. Okay, so we have the optimal level of input that is a function of price of input 1, input 2, and also output produced. And if you calculate it specifically, you're going to obtain this one. The ratio between W2 over W1 to the power of 1/2 multiplied by Q to the power of 1/2 gamma. Okay, what about Y2? That is also a function of W1, W2, and Q. Remember W here are prices of inputs. Now this one becomes W1 over W2 to the power of 1/2 multiplied by Q 1/2 gamma. Okay. Now, if you have these two, demand for input here, what you can do is that, similar to the expenditure minimization problem in the utility analysis, we can come out with what we call cost function, indirect cost function. Okay, then you know that cost function here in this case is depending on W1, W2 as well as Q. So if I simplify it even further, we know that it is W1, Y1 star. This is the optimal level here when we put the star, W2, Y2 star, and specifically we obtain this C as a function of W1, W2, and Q equals to. Now I'm not going to show you the algebraic, manipulation of this, but you need to find it. But I show you the final results here. But of course, you need to show all the steps when it comes to exercise. Here, I just jump the step. So we have to multiply by W1, W2 to the power of 1/2 or square root. Okay, and then multiply by Q to the power of 1/2 and then gamma. That's it. All right. So this is the cost minimization function. So when we have this cost minimization function here, what we have here is that this is the minimum cost incurred by the firm if the firm hires, Y1 and Y2 to produce Q. Okay. So this is the symmetry Cobb-Douglas example here. Now, let me give you another example. In this case, if we have perfect complement, this is second example. So this one is the first example. Now, let's move to second example. Let me write the question first. So, let's say we have a perfect complement. We also still have two output here, and we have production function. Okay, Q equals to a function of Y1 and Y2, but specifically we want to minimize the quantity of Y1 and Y2. Okay, then we can have complement, perfect complement. Now, so here, if I try to show you in the form of graph, when we have perfect complement, this is just revision, yeah. So you have y2 on the vertical axis, y1 on the horizontal axis. Both of them are inputs. Okay, so this is isocos. Okay, isocos, and then this is the isocon. So the isocon here shows you that if I want to produce using y2, I must have y2, let's say a. I don't put number. This one is y1 a. So in this case, the complementary is when we have production that occurs at the vertex of the L-shaped isocon. So you see the isocon here is L-shaped. So this one is isocon. Okay, so the vertex is here at the minimum point, or at the point that join the two different lines of L-shaped isocons here. That means in this case, minimization is y1 equals to y2 at what point here? I call it point x, at x. All right, now so we have the constraint. That is output function. Okay, so y1 equals to y2 must be equal to q also. Okay, so here we have cost function. C is a function of w1, w2, and also q. And then we know that w1 multiplied by y1, w2 multiplied by y2, sum both of them. And then we have, because y1 here equals to y2 equals to q, that's the constraint here at this point, then we just easily substitute it with q, w2 also with q. You simplify it even further, factorize it, because the common factor now is q. Now we have this cost function. Okay, so that's it. Now this is the perfect complement example. Why don't you try to find the example for CS function, typical CS function and other types of function, okay, for your own exercise. And from here also you try to find out about the Hotelling lemma and Shepard lemma and whatnot. So when it comes to Hotelling lemma, Shepard lemma, isocon, cost minimization problem, which is analogously can be compared with expenditure minimization problem in the utility analysis, then I want to look at again comparison between firms and also consumer. So when we talk about firms, I did mention to you earlier, but this time I just want to summarize a bit more. Consumer, okay, so we have cost function. And the cost function here is written as W1 Y1 plus W2 Y2. This is for the two case, yeah. Until, let's say if we have too many, until plus Wn Yn or Wk Yk. Let me use proper notation so that you are not confused with the lecture note. And here, so K. All right. And for consumer, we have expenditure function instead. So expenditure function, here we have cost function for the firm. So for expenditure function, the function looks like this: P1x1 plus P2x2 plus, until the last one, Pn xn. Okay, now solution that we get, this is number 1, number 2, yeah, number 1, number 2, number 3. The solution that we get is basically, in the case of the firm, we call it conditional demand. And conditional demand here is y as a function of w and q star. Okay, but for consumer, we have utility function, and for our utility function it is like this, isn't it? And from there we can get Hessian demand function. Okay, and then we also get indirect expenditure function, which is E as a function of P and also utility, price of product and also utility. Now for here, from Y star here, we can get cost function, indirect cost function, which is C as a function of vector of W, prices of input and also the product quantity. All right, so I hope this is clear for you. And let's crack on. I have another last bit here for you to think and also for you to analyze. The last bit here is what we call return to scale. If you read the textbook, if you read other lectures, lecture note, the concept of return to skill, what they do is they teach it from the beginning. But here, I just want to introduce to you the production function first until you get the idea. Then only I introduce to you or revise again the concept of return to skill, because this concept is not something new. Yeah, because in your principle of micro in the first degree, first year, you should know this one already. Okay, now when we talk about a return to scale here, we have what we call constant return to scale, decreasing return to scale, and also increasing return to scale. Now, before I explain to you all of this, let me draw some simple graphs here for production function and also other thing. Let me draw it properly here, it's not nice. All right, so here the first one. So I have production function here, which is concave, output is Q, and then Y is input. So this, okay, similar to the Solow model. And then we have the cost function, which is this. So I have quantity of output, yeah, not input. Let's say shoes, Q is shoes, pairs of shoes. And then the pound sterling here. And then I have my cost function, which is increasing like this, but obviously convex. Okay, so if I put a line here, the slope is this. So this is this can help us to calculate the slope, which is MC. Okay, now if I have another one here, so here I have pound sterling. It will also quantity of output. Then my MC looks like this, which is a function of Q. My AC looks like this. Okay. Before I forget, let me use red pen here. For this, if I take one point from the origin and take another point from here, join them, I get a straight line. Let me fix the line. This is not very nice drawing though. Okay. Then the line here is above the black curve. Then this is basically the average cost. Okay, slope, which is the average cost. All right. Now, if you look at Fy here, the production function, yeah, Fy here is concave. Okay, what's the implication of concavity of Fy or production function? Then we're gonna have cost function, which is cost function as a function of price of input W and also quantity of output, which is convex like this. Okay, convex in Q. So we have convex in Q, and then we can see that the MC is increasing. Okay, increasing as we increase the output, as we increase the Q. So MC is increasing in Q. So in this case, concave production function in the first graph here, okay, leads to the cost function, which is convex. Concavity of the cost function, concavity of the production function here leads to what we call diminishing return to scale. Now, when we talk about diminishing return to scale, it means what? It means if we double input, output will increase less than double. That's a very typical definition that you have learned in the first degree. So that means more input needed for each unit, okay, of output Q. And this leads to the rising costs of production. Okay, now, but then at the same time, because of increase in the cost of production, therefore you can see average cost is also rising. So because this one exhibit decreasing return to scale, that's why you can see MC is increasing, AC is rising, because now remember, when you double your input, your output produces less than double. So that means your average cost is increasing because quantity now less, but cost is increasing. You still have to pay more the cost of input because you hire them, even if your output produces less than double. Okay. So here, doubling input produce less output, so average cost increases. Okay. So this is what we call decreasing return to scale. Now, what about increasing return to scale? What about constant return to scale? Can you find out? So here, you have production function, you have cost function. You have learned cost function. but I didn't explicitly explain to you which one is the properties of cost function. So I want you to find out the properties of cost function, especially when it comes to homogeneity degree of the cost function, whether it is concave or convex in price and price of output and input and whatnot, and compare it with the production function. This may be questioned in your assignment or in the quiz, last quiz, which is quiz number 2. All right, guys. So these are the things for theory of production. Although some of them are analogously can be compared with utility function, but of course they are two different things. You have to remember consumer is consumer, production is production. Compared consumer and production is clearer in terms of visualizing all the things. But consumer, because the utility itself or the satisfaction itself is not easy to measure, then it becomes an abstract in terms of calculation. So I hope you do a lot of exercises and whatnot, and this can help you to understand better. Okay, so thank you.